4.4 continued on curve sketching and concavity. This one will be just basic curve sketching. So let's look at this example. 1 minus the cube root of x, or x to the 1/3, and find local extrema, intervals of concavity, inflection points, and sketch. So this one first, we may want to look at it like this just to begin with, because we know that basic shape actually. So sometimes you can verify the calculus. So let's do that first. So let me back that up. Your basic function is, let's say, g of x is the cube root of x. So that's like your parent function. And so for a cube root, you may remember, it's going to look like this. So you have x and y, and so your cube root is this function. And it's essentially the inverse of the cubic. And so it goes vertical right here. You got a vertical asymptote, or not really an asymptote, but the graph goes vertical right at 0. And so if you looked at tangent lines, they continually increase, and then right at 0 you'd be infinite, and then they go real steep, and then they start to decrease like that. So we know that's basically what it looks like, and then this thing is shifted. So if you said y equals negative cube root, that inverts it. So the negative cube root is going to do this to it, and it's going to be like this, basically. And then the 1 is another shift. So if you say y equals negative cube root of x plus 1, it's going to shift everything up 1. So your basic graph then is going to be like this. So that's what we should end up with. We should end up with a y-intercept there, a root here, which we'll calculate pretty quickly. And then it looks like we're going to get an inflection point somewhere in here. All right, so extrema, are we going to have extrema on this? We shouldn't, right? We should get no extrema. So this is kind of ahead of the game here, but I want, sometimes you can analyze it before you get started on what's going on. Okay, so let's just keep that for now and see what we get. So now you have to show it. You have to verify what's going on. You can't just graph it. I don't really care about the graph. We want to see that your work demonstrates the aspects of the graph and kind of like proves it. Okay, I gotta change this to an arrow. It's bugging me right there. Oops, I erased the whole thing. Didn't want to do that. So this, I don't know why that turned out like that. That's just a arrow of some sort like that. Okay, so that's what the negative will do. We'll flip it like that. Okay. All right, we'll come back to this one to make it look a little nicer here and there. All right. So that's just how you would analyze that basically in college algebra, or just algebra. That's how you'd analyze that sort of thing. Let's take a look now at taking derivatives and stuff. So you have your function f like this, and then let's take the first and second derivatives. So f prime of x is equal to negative 1/3 x, and then you subtract, right? So it's x to the negative 2/3. Okay, and then you may want to write that as take away the negative exponent, because we want to know that that's what you get. You get a 3 down here, x to the 2/3. So our only critical value is 0. Critical value is undefined at 0, so it's just 0. Let's go ahead and do f double prime. So f double prime, multiply that, and you get positive 2/9. Subtract 1, and so you get 3 minus 3, so you get negative 5/3. And so you get 2 over, so it's positive 9x to the 5/3. And our critical value for a possible inflection point is also 0. So that's all you're really getting. So we know what it looks like, but you still still want to test it and look at it, see what's going on. Let's do intercepts. So x-intercept next. Set f of x equal to 0 and solve. So that's equal to 0 if and only if, and then our function is there. If 1 minus x to the 1/3 is equal to 0. So x to the 1/3 equal to 1, equal to 1. And so x equal to 1. So 1 is a root. So 1, 0 is the root or x-intercept. Okay, and then y-intercept. Oops. Y-intercept will do f of 0. And you get, where's our function again? And you get 1. So 0, 1 is the y-intercept. Okay, so let's analyze this a little bit using our derivative. When you have this square here, then you know it's positive. And so we can just argue that f prime is always negative. So no matter what you put into the function here, you're going to end up squaring it and makes it positive. But you already have a negative hanging out. So that means your f prime is always less than or equal to 0. So we can state that. So f prime of x is less than 0 for all x in R, excluding 0, of course, because it's not defined there. But it doesn't change from increasing to decreasing or vice versa. So that implies no extrema. All right, so no extrema there. So it's always decreasing, and let me use my abbreviations because otherwise it gets too messy. Always decreasing. What about inflection points? Okay, so let's test CVs for inflection points. So that's around 0. So now you're looking at this, and it's positive. So when you put in it, and then 5/3 as a power will make it negative. Like, I mean, if you put in a negative, it remains negative. You put in a positive, it remains positive. So it doesn't do anything to the function. So f double prime of -1. So let's just test x equal to -1. So f double prime of -1 is less than 0. And f double prime of +1 is greater than 0. Okay, so that implies inflection point. Let's just abbreviate, make it simple on us. That implies inflection point. So 0, 0, 0, 0, oops, not 0, 0. 0 f of 0, which is 0, and what was f of 0? A0, 1. 0, 1 is an inflection point. We can analyze a few other things. We could look at the limit of f of x as x approaches infinity. So we could look at the function value, what happens, and basically this approaches infinity and it's negative, so the whole thing approaches negative infinity. Okay, so it just goes down forever. We can also look at the negative infinity limit of f of x as x approaches negative infinity equals positive infinity, because it becomes a positive positive, or negative negative becomes positive. That's what I mean. Okay, so those are other things you can analyze. That's another way to analyze. What am I thinking? Analyze asymptotes, horizontal asymptotes. So this is what we call end behavior. That's like in quotes. You never get to the end because of infinity, but just like at the ends, what's going on? That's really the idea. Okay, so we can now graph and label that stuff. So we have our graph. We know what it basically looks like from above, but now we have our proof basically. So we'll make 1 here and then 1, 0 here. It's coming in like this. And then it comes down, and it actually goes vertical, so it's kind of hard to draw, right? Wait, what was it? What's the inflection point again? Inflection point at, it's 1, 0. At 0. So we want to make it look kind of more like that. So I had it a little off. Let me change my eraser and erase all the, there we go. So it's going to come in like this. So right here, it's going to go vertical and come back. So it's more like that. And then it just approaches infinity like that. And then this comes down, goes vertical, then it starts to flatten out a bit. So that's close. That's pretty good, I guess. Inflection point, label that 0, 1 and 1, 0. Okay. Very good. Let's do another one. Next example. Let's see. Here we go. Let's let f of x equal x to the 2/3 times x plus 5. Okay. So same thing as above. I'll just write that down. So same directions as above. All right. So that's what we're looking at. Okay. So let's, one thing you can do on pretty much all these is just start taking derivatives. So let's just do that. I messed around with this thing before in the past, and in reality, it's actually better on this one to not distribute that and just use the product rule. Turns out it's a little easier to manipulate. So let's just do that. So you know, and a lot of math is about trying one thing, seeing what works. You know, you don't have to use the same thing every time. There's you know, it's not about how fast you can do these at all. It's about analyzing things. All right, sorry, I had to take a drink of water. So same directions above. Okay, so derivative of the first would be 2/3. And then subtract and you get minus 1/3. Times the second. Plus the first. But see, the derivative of the second is just 1. So you can leave it like that. And so now you can just treat this as, and let me move this. We have plenty of room to work with here. We can write that as 2x plus 5 and then over x to the 1/3. And then we'll say plus x to the 2/3. But you can see here when you add that up, let's use a different color. You have x to the 1/3. Yeah, let me fix that. So you have x to the 1/3, x to the 1/3. When you simplify this, you get something kind of nice. So you get 2x plus 5 plus just x over x to the 1/3. And then we've got to simplify that a little bit further. So we get 3x plus 10 over x to the 1/3. And that's more difficult to do, actually, if you, well, not, I wouldn't say much more difficult, but if you use, if you distribute this thing, then you got to combine it later, which can be a little more difficult sometimes. So you can simplify that. There's something wrong with that. Hold on a second. 5. Oh, I know what it was. There's a 3 here. This needs to be a 3 down here. And so this needs to be a 3. So 5. So it's a 5 like that. Okay, so now you can factor out the 5 and have x plus 2 over x to the 1/3. And so now you have critical values pretty easily. So so set that equal to 0, solve. So you say equals 0. Okay, and so that implies x is -2 and x cannot be 0. So we have those two critical values to check out. All right, so we'll leave that there. Let's go ahead and do f double prime of x. So f double prime, we go ahead and do the derivative again. And we can, you still actually could just use this form. What did I end up doing? I think I went ahead and used the first form. So where did it go? So let me just show you what I did. So you kind of depends on how. Actually, it's probably a good exercise just to show you this form anyway. So if you wrote this as 5/3 x to the 2/3 plus 10/3 x to the -1/3, because that's f prime. Now you can take that derivative directly. So that's just basically taking this and dividing it by each, well, actually this one, dividing by each term. And so here's your -1/3, and this is a 1, so it's 1 minus 1/3 is 2/3. So this time, you could use quotient rule. So that's kind of up in the air, right? I mean, do you want to just use regular power rules to do the derivative and then combine back, or you could use that and just do quotient rule. So let's just do quotient rule. I think that's probably easier. I don't know. So derivative of the top is just 5 times the bottom minus the top, so that's 5x plus 10, times the derivative of the bottom is 1/3 x to the negative 2/3, all over the bottom squared. So it's x to the, and if you square 1/3, you get, I'll just write it out. So you get 2/3. So you still got to simplify all that. All right, so we want to work with that and simplify it. So it's 5x to the 1/3, and then minus 5x to the, so it's, you're adding that up, so it's 3/3. Oh, it's actually 5/3 there. So I distributed, now I'm distributing this across like that. So you get 5/3, and then it's x to the 3/3 plus 2/3, so it's just 1/3. It's a positive 1/3. And that's minus, and then another minus, because you're taking this along to the other, to there as well. And so that's 10/3. And then that's the same, x to the negative 2/3. And that's all over x to the 2/3. So this will take some work to simplify. I think the other 4 might have been better. now that I look at this. But that's okay. That's what I meant earlier, is you gotta try different methods and see what works better. So now just add this up, right? So you have basically 15/3 minus 5/3 times x to the 1/3. So you're adding those coefficients. So that's going to be 10/3 x to the 1/3. So it's 10/3 x to the 1/3 minus 10/3 x to the negative 2/3. So you can, let's see, there's something else going on there. Well, let's continue. I'm not sure where we're at there, but you get the x at 2/3, and you can divide that to both terms and then subtract, see if that's going to help at all. Let's erase this, see what's going on here. So that's, so you get 1/3 minus 2/3 is negative 1/3. So 10/3 x to the negative 1/3 minus 10/3 x to the, and then you get negative 2/3, and you subtract another 2/3, you get negative 4/3. Like that. And I'm missing, let's see, something with the 3. I'm missing a 3. How did I do that? So I distributed that. I get 5/3, 3/3. Yeah, I don't see it. There's something else I'm missing. let's continue to simplify. So it's equal to 10 thirds. And then this is 1 over x to the 1/3 plus 1 over x to the 4/3. And so you get 10 thirds. And so you want to treat that as x to the 1/3, and then that's would be a 4 there. So when you factor this thing, put it like, do it like this. Multiply by x. So when you add that up, you get just x. So if you do x over x, that's what I was trying to show you. So you get 3/3, so that's 4/3. So you get x minus 1 over x to the 4/3. And so because this is a 1, which is 3/3, so it adds to be your 4/3. So just be careful with that. This is all scratch work. I don't need that there. Okay, so your critical value for that then is 1 and 0 again. And that's pretty much going to happen. If your first derivative, you get 0, second derivative will also be 0 as critical value. And you got to figure out what's going on there. Okay. I was looking at my algebra here, or arithmetic. Let me just double check something. I don't want to pause the video. Looks like something might be wrong with the 3, but it's not going to change our solution, ironically. But let me double check. Nice square. Okay, so derivative, let me come back here. Derivative of the top times the bottom minus the top times the derivative of the bottom, 1/3, and that's right. Then I distribute and I get 5/3, 10 thirds. 5 minus 5/3, so 3 over 3 is 10 thirds, which is that. And that's 10 thirds, so I can just factor out the 10 thirds. And then it's, oh, then I have to divide. So no, that 10 thirds looks all right. It looked different earlier. Well, I don't know. I'm going to have to just keep going because I don't want to redo the video. So that could be wrong, but it's not going to change our solution. I don't know what I'll do. All right. So let's just continue with what we have. Test our critical value equal to -2. That was back here earlier. Because we can. So we can, this is one of the things I wanted to show you is where you have f prime is 0, we can use the second derivative test. So this is the second derivative test. So I actually said that. So using the second derivative test, we have f double prime of -2 equal to 10 thirds, and then it's -2 minus 1 over something positive, which is less than 0. Okay, so if it's less than 0, it's a concave down. Implies concave down, right? So it's like that. Okay, therefore, what is that? Therefore, it's a local maximum. That's how I want you to remember it, the concavity of it. Okay, and then calculate f of -2, and you can approximate if you want to, because I think it's more difficult. All right, so for c equal to 0, we can't plug it in because it's undefined. So apply the first derivative test. So first derivative test, we're plugging values around 0, but not all the way to -2. So we want to test left and right of 0. So here's 0, and then our -2 is down here. So you want to pick, like 1 and -1. So those are the values you want to test. So you want to do f prime of 1, and we go back to f prime, which is way back up here. And so f prime, here we go. We have, oh, I know what happened. There's a 3 here. That 3 there. Which means there's a 3 here, 3 here. So this ends up being a 9. So that's where that went. So I found it. We might find it eventually. You see it doesn't actually affect our solution at all, but except it would affect our no, it won't even affect our function value, but oh well. Okay. A little longer than expected, but that's okay. All right. So you test that f prime of 1. So you're just looking for positive or negative, right? So you go back. So f prime of 1, everything's positive, so it's positive. Okay, so we'll just say, wait. Yeah, positive over positive is positive. Okay, so increasing. Well, you're supposed to go from -1 to 1, right? So let's do it like that. So you're going from left to right. You want to see what's happening. So -1. Let's do -1 first. So you get a positive over a negative, which is a negative, so it's decreasing. Okay, then you do f prime of 1, and you get a positive over a positive, which is positive, so it's increasing. Okay, so you go from decreasing to increasing. That does imply a local minimum. So you go from decreasing to increasing. It's probably a inflection or not an inflection point. It's probably a cusp. And so you want to check, see if it's a cusp. So you want to do the limit of f prime of x as x approaches 0 on the left and then right. Limit of f prime of x as x approaches 0 on the right. And so let's go up to our derivative. Where's our derivative? Derivative is right here. Okay, so on the left, you are like negative values. Let me see how I analyze that sucker. Okay, I'll come back to that. Okay, let's come back to that. All right, so then let's do intervals of concavity. All right, so intervals of concavity, we want to test around the possible inflection point. So it's negative infinity to 0, 0 to 1, and 1 to infinity. Okay, so then you test f double prime of x. Negative, negative, so nothing there, but at 1 you do get something. You get a positive. Okay, so x equal to 1 is an inflection point. Okay, so we got an inflection point at 1. All right, so then we have our roots. Okay, so now we want to piece this together. So we have our roots. Can't keep scrolling back up. At negative 5, 1, 2, 3, 4, 5. So your root at negative 5. At negative 1, 2, we have a function value. So it's actually 1, 2, 3, 4.7. So it's right there. You'll evaluate that later and check it out. So f of negative 2 is approximately positive 4.7. Negative 5 is here. We have an inflection point at 1. And then f of 1 ends up being 1 plus 1 plus 5 is equal to 6. So it's 1, 2, 3, 4, 5, 6. So it's up here. The function f, so if you do the limit of f of x as x approaches infinity, you're going to get infinity. It just takes off, so it's going to just keep going. We think there's a cusp here, so we'll make that like a cusp, and then it maybe does something like that. So there's your inflection point. Okay, this is not a cusp. This is a local maximum, so it's probably going to do something like that and just come down. So let me go in and erase some of that. So I know that's going to be, I'm assuming that's going to be some kind of cusp because it goes from decreasing to increasing, but it's undefined there. Okay, so that's my hint. And just by the type of graph it is. Okay, right here is negative 2 and approximately 4.7. Okay, right here is your function value. There's your negative 5. So it's probably going to just, then as x approaches negative infinity, this is going to keep going down. Okay, so you can also look at the limit of f of x. And you can do this kind of stuff in your head. You don't have to show all this stuff, but stuff you want to analyze. This is going to go up like that, crest out, and then keep going down. So there's that basic shape to it. Like that. Okay. So inflection point, label that. Here's your inflection point. There's your local max. And then this is also a local min. And then right here. So this told us it goes from decreasing to increasing. So it's a local min. Okay, these, we'll analyze this later, but f prime up on the left will be negative infinity. F prime on the right will be positive infinity. So if you look at this, this is a negative slope, and it just gets getting really steep as you right, but it's negative. And then the other side will be positive. Go like this. And so when you get that,